Our recent class discussions have been about work and energy. Now, moving on to Chapter 5, we will focus on one particular kind of energy. And do you know what it is? Well, here's a hint. There's a pretty good, although violent, Robert De Niro movie with the same name. It's one word. Okay, if you don't know by now, I'll have to tell you. Our discussion in Chapter 5 is about heat. And in this introduction, we will look at temperature scales and phases of matter. Temperature is related to heat, but is not the same thing as heat. Surprisingly, temperature is a difficult concept to define, even though we're all familiar with the notion of hot and cold. It turns out temperature is one of those 7 fundamental physical quantities that all of physics is built on. Earlier in the semester, we discussed 3 of the others: length, mass, and time. Well, you might already be aware that there are 3 temperature scales widely used. These are the Celsius, Kelvin, and Fahrenheit scales, as illustrated here in the picture. The Kelvin scale is also called the absolute scale for reasons we'll mention later. Now let's look at how these 3 scales compare with each other. We start by noting where the freezing point and the boiling point of water at standard atmospheric pressure are fixed on each scale. The Celsius scale is fixed so that water freezes at 0 degrees and boils at 100 degrees. There's an interval of 100 Celsius degrees between the freezing and boiling of water. The Kelvin scale is fixed so that water freezes at 273 degrees and boils at 373 degrees. As in the Celsius scale, there are 100 degrees between freezing and boiling of water in the Kelvin scale. So, 1 degree temperature change in Celsius is equivalent to a 1 degree temperature change in Kelvin. Kelvin and Celsius are similar to each other in that respect, but they are different from each other in that the Kelvin scale is shifted by exactly 273 degrees relative to Celsius. Now, let's look at the right scale, the Fahrenheit scale. By right, I mean on the right side of the diagram, not the correct scale. We see that water freezes at 32 degrees and boils at 212 degrees. So there are 180 Fahrenheit degrees between the freezing and boiling of water, which means 1 degree change of temperature in Fahrenheit is just a little more than half a degree change in Celsius or Kelvin. Fahrenheit is also different from Celsius and Kelvin in fixing the reference point, i.e. the point at which water freezes. In Fahrenheit, it is 32 degrees compared to 0 and 273 degrees in the other 2 scales. Now, I suggest you stop the video and review for yourself what the freezing and boiling points of water are in each of the Celsius, Kelvin, and Fahrenheit scales, and then see if you can summarize how Celsius and Kelvin are similar and different with each other, and finally, how Fahrenheit is different from the first of these 2. Now, why is the Kelvin scale also called the absolute scale? And why is it shifted from the Celsius scale? Well, these 2 questions have the same answer. It turns out that temperature, i.e. hotness, has no theoretical upper limit, but it does have a lower limit. In other words, there is a point at which it is theoretically impossible to get colder. Now, this is a provocative thought, don't you think so? This lower temperature limit is minus 273 Celsius or minus 460 Fahrenheit. So, the Kelvin scale was fixed by simply shifting Celsius by 273 so that the Kelvin 0 degrees corresponds to this lowest possible temperature. So 0 degrees Kelvin corresponds to what is called absolute zero, the lowest temperature theoretically possible. Hence, the reason Kelvin is also called the absolute scale. Now, how can we think of there being a cold temperature below which nothing can get colder? Well, there are several ways to think about this. And let me just show you one intriguing idea. Let's start with an arbitrary volume of gas. Think of a balloon filled with air at room temperature. This is represented in the graph at the right. Now, what happens if we were to gently heat the air in the balloon? Well, you might know that things, especially gas, expand or get bigger when heated. So let's increase the temperature and remeasure the volume. Now be sure that you're looking at the graph. And if we did it again, being careful not to break the balloon, we would be looking. Now let's go the other way. That is, let's cool the air inside of the balloon from its original temperature and check the volume. Stop the video and predict what you think will happen. Okay, let's see if your prediction is correct. I bet it is. Watch the graph. Let's cool a bit more. Notice what's happening. We are approaching a point on the graph where volume is going to zero. Make sure that you can see that from the graph. Indeed, there comes a point where volume disappears altogether. That point is 0 degrees Kelvin, or absolute zero. There is no physical meaning to a colder temperature, since negative volumes are impossibilities. Pretty interesting, wouldn't you say so? Let's look briefly at the three phases of matter and the physical processes occurring when adding heat to a substance that is in one of its three phases and then makes a transition from one phase to the next. To be sure, we think of matter as having three phases: solid, liquids, and gases, although we could also talk about a fourth phase called plasmas if time allowed. We will use water as an example, but the principles generally apply to other materials as well. Let's start with solid water, i.e. a block of ice, at some temperature below 0 degrees Celsius. Remember, 0 degrees Celsius, not Kelvin, is where water freezes to ice. Now we are at the bottom left portion of the graph that is tracking temperature in response to heat energy that's being added to the ice. As we add heat, the temperature of the ice increases. It is still cold, but it is increasing from a negative Celsius value and is approaching 0 degrees Celsius. Then at 0 degrees Celsius, which is point A on the graph, look what happens. We keep adding heat energy, but temperature does not change. What? Indeed, the heat energy goes into breaking the chemical bonds that are in solid ice and turning it to a liquid. That's happening all along A to B in the graph. Ice is turning into a liquid water from A to B. Then at B, all the solid ice is gone. It has melted. And we now have, at that point, 100% liquid water. As we add heat to liquid water, it raises its temperature, as shown going from B to C. And now, why do you think the graph goes flat again at C? Think about it. The liquid water has reached its boiling temperature, but needs additional heat energy to actually boil away and change its phase into a gas. So, from C to D, we keep adding heat, but the heat energy does not increase the temperature. Instead, it goes into breaking the liquid water bonds, thus creating a gas. And what has happened at point D? Bingo! If you suggested, all the liquid water has now turned into a gas. Adding further heat then allows us to heat the gas, as illustrated in section DE, if we were to be able to capture that gas. In review, where the graph shows an upward slope, we have the water, be it liquid, solid, or gas, changing temperature, that is, heating up, while entirely in one of those three phases. Where the graph is flat, we are still adding heat, but the added heat does not change its temperature. Instead, the heat goes into changing the phase of the water from one of its phases to the next. Interesting. And what might we learn about cooking with hot water from this? Well, we'll discuss that in class. I can hardly wait.